Okay, so the idea for today, as I was telling you last time, um, well, just to summarize a bit like of what we have been saying. Oh, I haven't turned on the projector. And I haven't connected this. This is, let me stop sharing and try it again because like it looks smaller than usual. What's happening here? Okay, now that does look better. So essentially, again, like what we're trying to understand in this course is how to like maximize or minimize one of like these like linear functions. So what we're trying to know, like figure out is what happened to the color black. Mhm. Our goal like is to is to find max or mean, like it doesn't matter which one. I'll tell you why like later. Um, but you want to find like the max or mean of a function like um, C1 x1 plus C2 x2 plus C3 x3, blah, 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 Cn xn, where like x1, x2, x3 up to xn satisfy some inequalities. Linear inequalities. Which I gave you some examples with like the farmer's problem in the first two classes of how those problems typically look like. Uh, what what happens is like again, there's like a method to kind of like find the max and the mean in a pretty systematic way, which is called the simplex method. But before getting there, it is worth like it is convenient to have like some basic terminology about the properties of like the sets that satisfy like the inequalities. Okay, so the thing is like these in like when you have like for example like in the farmer's problem we had 0 less or equal to x1, 0 less or equal to x2, then x1 less or equal to 3000, x2 less or equal to 4000, and we had x1 plus x2 less or equal to 5000. So, right? So like you have like all these inequalities, and the thing is like when you draw those inequalities on the plane, they do have like a particular shape that has like many useful geometric properties. I think in this case, like in the farmer's problem, I may be getting it wrong, but I think it looked like more, it kind of looked like this. Okay. So the thing is like all these inequality, if you just focus on the inequalities and you don't care about like the function for now, like what just like the inequalities per se do have like interesting shapes and they do have like some common features. And those are kind of like the ones that we have to study first before like discussing how to like find the max or the mean. Okay. So basically what they have in common, like all like this in like like the solutions to the inequalities is that they form like a convex set. So that's kind of like what I was going to start with first, telling you what's a convex set, what are some properties of those, and then how that would relate to like our original problem that we want to understand. Okay, but so So like the point is like the regions that satisfy the inequalities, regions which satisfy the inequalities have some nice properties, some nice features. Um, which like the nice feature is called convexity. Okay, so let me tell you about that, what convexity means, which because probably it's like a word most of you haven't heard before, but it's kind of like one of the in general in mathematics, convexity is one of like the best things you could have. So it's kind of like a very convenient thing to possess. Um, So before telling you about what convexity means, I do have to remind you about like the equation of a line. So a little bit of like a throwback. So I'll draw the picture in 3 dimensions because that's kind of like the most like we can do, right? But let's say you have a vector which I'll call x1, okay? And then you have a vector that you have called x2, right? And the way I'm drawing the vectors, like you have to imagine that they start at the origin, right? And they just like end at a particular point, which is like why I'm drawing these dots here. So that is where like the vectors end. Now between those two vectors, right, there is a vector that connects these two, which you could draw. And that vector is just x2 minus x1. That's like the vector that that goes from x1 to x2. And that is more or less like obvious depending on how much you remember how like the vector addition looks like. But the idea is like when you add vectors, you know, sorry, just to remind you about that. Oh, let me put it here on the board. But the idea is like when you have a vector u and a vector v, then the sum of them corresponds to the third side of the triangle. So like the sum, like the vector addition corresponds to the third side of the triangle. So if you remember that, then this is not too bad to convince yourself of. Because if you have like it's kind of like, this is kind of like U and V in the diagram that I'm drawing here. So if you do x1 plus x2 minus x1, the x1s cancel, and then you just end up with like x2 here. So that's why like, the vector, like the difference between vectors corresponds to kind of like the displacement between two points, like if you want to think about it in that way, which is like a formula that is particularly used like in calculus, like a lot, like in multivariable calculus, if you are trying to find the equation of a line, for example. Okay, so that is kind of like the vector that connects the 2 points. So just imagine that I multiply this vector by a quantity, like I rescale I rescale this vector. Okay. I'll make a copy of this. So just to start with something concrete, you know. Let's say, for example, I multiply that vector by 1/2, right? So if I do 1/2 of x2 minus x1, what is that vector? It is literally, it points in the same direction as x2 minus x1, but it has half the size. right? So this would look more or less somewhere like that. Half the size of the vector, right? Is that making sense? And then, and if you multiply by a number between 0 and 1, not necessarily 1/2, but if you multiply by a number between 0 and 1, then, it just like will land somewhere in here. Like, if it's like a third, it would be somewhere in here. If it's 3/4, it's closer to x2. So in general, if I'll call it a lambda because like that's like the usual name for it. If lambda is between 0 and 1, then how does the vector look like? Then lambda times x2 minus x1 looks like this. Right, so like again, when you multiply a vector by a scalar, like lambda is like a scalar, it has nothing to do with eigenvalues, by the way. It's just like usually like the scalars sometimes are called either t or lambda, depending on what you want to think about. But when you multiply when you multiply a vector by a scalar, it just changes its length, the direction is preserved as long as like the number is positive, like scalar. So if lambda is between 0 and 1, then the only thing you're doing is like you're shrinking it basically because the number is less than 1. So like the length gets shrunk. And so like, again, like for 1/2, you got this. For 1/3, you get maybe this. For like 3/4, you get this. Like, it's like, but like it's kind of like you play if it makes sense what I'm doing. You're like you have like this vector and then like the rescaling kind of like just shrinks it by a certain amount. Okay? Does that make sense? Kind of like so far so good. Questions up to this point. Okay, and so why am I doing that? Because now this new rescale vector, right? Like the rescale vector, by the way, the extreme cases are well, I'll say it in a moment. It's better to kind of write the formula first completely. So if so you have like the red vector, which is x1, the blue vector, the rescaled version of the blue vector, which is lambda times x2 minus x1. So again, if you were to do the vector addition, like the vector addition to remember, like you always have to remember that that corresponds to the third side of the triangle, right? So the vector addition, like this third side of the triangle would be x1 plus lambda times x2 minus x1. And in fact, I can erase this one because I'm no longer using it. Okay, just to make the picture less confusing. So like I'm adding the two vectors and I get like that purple vector there. Okay. And so I should have done this like as an animation. Let me see if I can give me a second. Let me see if I can find one here. Uh, yeah. Let me go. I mean, I think it's less confusing just like by seeing it first, like on like an animation. Um, so okay, right. So you see, like we go. Well, I could have like done it before, but like that's okay. Well, yes. Before, what I was saying is like, this was like imagine this was like x1, this is like x2, right? So when I choose 0.5, right, like the vector, like you know, where did I have it here? So this was x1, right? This was x2, and what I was saying is that when you choose like 0.5, like the vector was half the connecting vector, right? And so when you add these two together, right, this vector like kind of like ends at the midpoint between these two like vectors, if that makes sense. So that's why you see like the vector here like in between. And if you kind of like, if for example, ooh, what happened there? Let's see if this like, okay. If you shrink, like if you make what I'm calling lambda, but in this animation is called A1. If you make it smaller, okay, like this is going the opposite way. As like I would like it, but that's fine. If it's, I mean, if you make it closer to either 0 or 1, you get closer to one of the 2 points. Okay. But the idea in this case is like you kind of like, by changing the parameter like of t from 0 to 1, you're kind of like moving through every point in the segment that connects these two, if that makes sense. So it's kind of like let me write it on the board. So what I'm saying is that there is this segment between these 2 points, or like the endpoints of the vectors, if you want, if you prefer to think about it in that case. So there's this segment between these 2 points, and this vector is all like this vector x1 plus lambda times x2 minus x1 is always somewhere on that segment. So it always terminates on that segment. So it always like the endpoint of this vector is on the segment, is somewhere on the line segment between x1 and x2. Is that making sense? Kind of. I'm trying to find like an equate, like maybe I should have said it earlier, but I'm trying to find like an equation for the line segment between 2 points. That's kind of like what I'm trying to do. So like if you, I don't know if you have taken multivariable, because this is where like you would have seen this. You would know that the equation of a line is point plus d times a vector. So this is kind of like where it's kind of coming from. But again, the point is like if you combine the vectors in this way, then like if you combine this like x1 and x2 in this way, you always get something in between them on the line segment between them, as long as you use like a rescaling that's between 0 and 1. Now, in practice, um, like the way in which this is usually written in a more convenient, nicer way is like, you know, if you like just distribute the lambda, this is lambda x2 minus lambda x1. And then you factor out like if you factor out the x1s for the first and last terms, you get like 1 minus lambda times x1 and then plus lambda x2. Okay. So this is kind of like the way to write so what I'm trying to say is like the equation for the line segment between 2 points. So what am I trying to find? So the equation for the line segment between 2 points x1 and x2, or two vectors, is represented by 1 minus lambda x1 plus lambda x2, or lambda between 0 and 1. Okay. Maybe it's better, like, I'll do it like again, but like with this formula, like the one I want to do it. Okay, let me move this around. Again, it's like an animation kind of like helps more than anything else I could show you right at the moment. So, oh my God, this was from Calc 2. So for example, let's say that one point is 1, 4. And let's say that the other point is 3, comma 1. Okay? So where's the eraser here? Here we go. So what if, like, think of x1 as 1, 2, think of x2 as 3, 1. And so what is like that coming? Oh, like I think I moved the algebra. I think you can still see the iPad. Sorry, let me share the. I just wanted to share the algebra. Okay. So if I do what I had before, like 1 minus lambda x1 plus lambda x2, what is that equal to? It's 1 minus lambda times 1, 2 plus lambda times 3, 1. Okay. So like you multiply a scalar by a vector just by multiplying the individual entries, so you get 1 minus lambda, 2 minus 2 lambda plus 3 lambda comma lambda. Okay. And that gives you what? It gives you 1 plus 2 lambda. And then 2 minus lambda, if I'm not mistaken. That makes sense, like that's what the answer gives us. So I'll just put in like this. Well, in this animation, I'm going to use t instead of lambda. But so let me put like r. Let's see. You know, r being like 1 plus 2t comma 2 minus t. Okay. And so you see here, that as I change the value for t, the point R is kind of like, well, it's moving between P and Q. If I choose numbers larger than 1, then I continue on that line segment, right? And if I choose values like less than 0, then I kind of go in the other direction. But they are always kind of like on the segment that connects the points, right? So if you kind of like do the line segment between the points, right? You will see that R kind of like always moves on this line segment, which again, like as long as t is between 0 and 1, if you allow for larger values, you kind of like continue on the line. Okay. But that's kind of like a nice way to, like, the thing is like we only need like the line segment. We don't need the entire line. That's why I kind of like restricting the t to be between 0 and 1. But if you wanted more like if you wanted like the entire line, you just like let t take any value, or lambda in this case. But so like that is how like so if you have 2 points, that is how you would describe the line segment between those 2 points. It's 1 minus lambda times 1 point plus lambda times the other point. Does that make sense? Questions about that? Okay, so why am I talking about this particular topic for now? Because that's related to this concept of convexity. So like I'll explain what convexity means right just now. So let's see. Okay. So the idea is that a region is convex or like well let's say you have like again I'll draw the picture in like R3, but like it doesn't have to be in like R3 or anything like that. So I'll draw like something that looks like a sphere. I'll draw something that is actually convex, but so let's think of like, like I'm thinking about like my region as like being like the inside of this sphere. So, and I'll call this region K um, for convexity, which sounds weird, but it's just because like the German word for convexity starts with K and like a lot of this stuff was developed by Germans, I guess. So a region is called convex if it has a property, the property that for any 2 points inside this region, let's call the points P and Q inside this region. The line segment between those 2 points is entirely contained inside the region. The line segment, like, let me actually start drawing the picture. So if I have a point P here, let's see. I have a point P here, and I have a point Q here, right? So what I'm saying is that I can connect them with a line segment, right? And if that line segment can be drawn entirely inside the region, then the regardless of which points I choose, then the set is called or like the region is called convex. So okay, so let me try. It's always easy to do like examples and non-examples to see what's going on. So it's easier to start with a non-example because like, okay. So here's like a non-example of what I just said. So take like on the plane, let's take the XY plane. It doesn't have, like, in fact, you don't even need to draw like the plane, like, um, like that's kind of like annoying. Let's say my set, let me do this a bit sharper just for is make my life easier. Okay, let's say my region or my set, like that's like, you could also call it a set if you want. Let's say like my region is this. Okay, so I could ask you just based on the picture, should that be convex or not? Right? And the answer is that it's not convex because, for example, if you choose these 2 points, right, try to connect them with a line segment, right? Sorry, like, let me use a different color. If you connect them with the line segment, right? Sometimes the line segment is outside the region, right? So like this is not, and again, because like the idea of convexity is that no matter which 2 points you choose, the line segments are always contained in the region. So you can never, they can always be drawn inside the region. So not convex. So like, of course, it doesn't matter. Like, here's like a point and a point. Like that line segment is entirely contained in the region. I don't care. I just need to find 2 points whose line segment is not entirely in the region for it to the convexity to fail. So like it is a strong claim because it's like no matter which 2 points you choose, the line segments always need to be inside the region. So not convex because the line segment from P to Q, P to Q is not entirely inside the region K. That making sense, kind of like. Let's do an example that is convex. Like for example, now here's like, and for now I'm doing it like more like proof by picture, because like we're just trying to kind of like get the idea of what convexity means. But like take like a right triangle, let's say. And the idea of convexity is like basically saying, okay, choose a point, choose 2 points, right? Is the line segment inside of it like the triangle? Yes. And it has to work no matter which 2 points you choose, right? So like that's the point, like that's like the idea of convexity. It has to be regardless of the pair of points that you choose, the line segment always needs to belong inside the triangle. So it doesn't matter. Like the edges are fine. Like so it's fine like if the line segment is kind of like on the boundary, that's allowed. So this triangle is convex. Convex because for any pair of points, the line segment is inside the triangle. That making sense? Okay, like of the picture. Here's another one. Again, we're just playing it by picture. So let's say I gave you a disk. What do you think in this case? Convex or not convex? Looks convex, right? Like, again, like it requires some imagination, but you imagine like choosing 2 points inside the disk or on the circle, like it can be on the boundary. Choose 2 points on the circle, and then you imagine connecting them with the line. And it does seem like all the lines kind of belong inside the circle. Like the proof is actually interesting if you want to do it like algebraically. I may give you like, may put it as a problem if you want to try it. But no matter which points you choose, like I'll do a few, no matter which points you choose, you know, the the line segments are always inside. So this is actually going to be convex. It actually works for like ellipses as well, like the ellipse with its inside. Although that actually, again, like if you kind of think about it, like it kind of makes sense, like in terms of the picture. But if you actually wanted to show it, it is a tricky thing. Like the easiest way to do it is like using some linear algebra. It's not like, not the, it can be, like there's sometimes like a difference between like doing like a picture and you kind of get convinced versus like actually doing like algebraically. Um, okay. Up to this point, are there any questions? So far, so good. Okay, so now I'm going to start getting to the reason why I'm doing this. So first thing, how does this connect with the previous stuff that I was telling you about? That this gives you like a formula to verify if you want to check that something is convex. So how to verify whether a region is convex or not? Well, what you can think of like is like if you had like a region, which by the way, this one is clearly not convex if you just look at it, like like convexity, like if you can see the picture, it's kind of you can kind of see it quickly, like most of the times, at least when it's 2D. 3D can be a bit more difficult. But this one definitely doesn't seem convex, but if if you wanted to prove that something is convex, you know, what you would say is like, well, let's think, um, I'll put like my axis here, like, let's think that one point here is represented by a vector x1, and let's say that another point here is represented by a vector x2, right? So you would need to show that for any 2 points or any two vectors that like lie that are inside the, so you need to show, let's call this K. You need to show that for any two vectors, for any two vectors representing points inside the region, the combination, right? Like the combination is in, we already have like an expression for the line segment between them. Oh, sorry, I was writing it like as 1 minus lambda x1 plus lambda x2 is also in this, is also in the region. Also represents a point in the region. Okay, so let's see. So for example, let me give you like it's not making sense why you would check that, because again, that like this expression represents, oh, like, and I should say for lambda between 0 and 1. So again, the idea is that this combination represents any point connecting the M, like, this combination corresponds to a point in this line segment. So if you're saying that something is convex, like this always has to be inside the region. So like that's why you need to check that this combination is always inside the region. But that has to be done for any 2 points in the region. Okay. So like the thing is like this property does interact nicely with linear algebra. So like, let me give you like an example of like the sort that we want. So I'll give you two examples actually. So let's say that you consider like the region, consider K, which are the vectors, like hopefully this notation looks familiar from like linear algebra, you know. So you're consider like you have like let me spell it out in a different way. You're considering like let me do like a concrete example. Let's say if you had like A to be 1, 1, 2, 1, -1, 3, and B what like times 1, 1, 2, 3. So like K would be the vectors what x1, x2, which solve the system of equations. What which solve? Oh, like this actually requires. Oh my God, I did it like I messed up the numbers. Like so, like x is the one that it requires 3 variables. Well, what is ax equals b in this case? It would be if you do the multiplication, it would be like x1 plus x2 plus 2x3. And then x1 minus x2 plus 3, x3 equals 2. So, I mean, or if you equate like the entries, like what I'm saying is like you're just looking at the solutions to a system of linear equations, right? So like it could be for like not necessarily this matrix and this vector, but you can consider like the solutions to a system of equations, right? Like that forms like a set. Okay. In fact, like maybe checking like if remark, like just to see if you remember this. If B is a zero vector, right? What was the name for K? Anyone remembers what name you give to K? What happens if V is a zero vector? You're considering AX equals 0, right? What was the name that you gave to the solutions to this system of equations? Yeah. Well, not that's not the name. I mean, like, this could still have like you depending on whether the matrix is invertible or not. That could have like a unique solution or not. Like, actually, yes, homogeneous. Okay, right. Like the equation is good. The equation itself is like a homogeneous equation, right? Because like a homogeneous equation was one where like all the entries, all the constants were 0. Good. But so like that's kind of like the name to the system of equations per se, right? But there was like a name related to that for the solutions to the system, like to the homogeneous system, not just like the name homogeneous system, but what was the name to the vectors? Yeah, sorry. Well, like that is more like related to the rank, whether like they're infinitely many solutions or like unique or not as if, oh yes. It is the null space, right? Like it was or the kernel, depending on how you saw that. But these, right? Yes. Like this was called like the null space and the dimension because it was a vector space, and the dimension of that was called the nullity. But the set K was called the null space, the null space of the matrix. Okay. So I'm just trying to kind of like remind you a few things like as we go along. Or the kernel. Like sometimes like it's also called the kernel. So I'm just saying like it is like a familiar thing, like it's just like vectors that solve like a system of equations, which if right, all these numbers are 0, 0, then like that does happen to be like a homogeneous system. Um, okay, so why am I getting to this? Oh, because it's actually like a good comparison. So if you remember, like the null space was a vector space or like a vector subspace, depending on how you want to think about it. But if you take a B that is not 0, 0, like not the zero vector, then like the solution space is not like a vector space. Because if you remember what it means to be a vector space in meant, it was like maybe a technical definition, but like that's kind of probably one of the most confusing parts of that course. But it meant that if you have two vectors, then their sum is inside the set, and they're like a rescaling of that vector is inside that set. So like the thing is like with the null space, that's fine. But like, if you had like something that was not 0, 0, when you add two solutions, like you don't get a solution to the original system of equations, right? Like now, so like these sets are not vector spaces in general, like that's what I wanted to say. So like, why am I mentioning this? So K is not a vector space unless unless B is identically the zero vector, but they're always convex. Okay, well, that is nice, but they are convex sets. So that means that if you take, that's kind of cool. I don't know, but what that means is that if you, like, let's make it more concrete. If you take two solutions, right, to the system of equations, and you take I didn't give the name of that. Like this is called like a convex combination. Sorry about that. This is called like a convex combination. If you take a convex combination of them, then that is still like a solution to the system of equations. So, so let me make it more clearly. Like, so what does this mean? It means that if x1 and x2 solve the system, solve ax equals b, then x lambda lambda x1, sorry, lambda 1 minus lambda, I keep putting it in the opposite. It doesn't matter in which order you put like the 1 minus lambda factor, also solves. So it means like if you have two solutions and you take this combination, then that combination is also a solution. Okay. And I'm about to check that for like, but actually, I don't know if you remember, like, when you study systems of equations, like first thing, the most important thing that they'll tell you is like a system of equations has three chances, like, or three possibilities. Either there's no solution, there's a unique solution, or there's infinitely many solutions, right? Like maybe you remember this. This is like actually a way to show it, because what this is saying is that if the moment you have two solutions, right, you can take a combination. Oops, like I'm missing a lambda, sorry here. Uh, the moment you have two solutions, if you had two different solutions, you could take a combination of this form, and that would also give you a solution. And since lambda is any number between 0 and 1, that's infinitely many solutions already. So that is like the easiest way to prove that the kind of like once you have two solutions, that jumps to infinite solutions, because, and again, like what is that representing? This is representing the segment between two solutions. Kind of like sounds a little bit weird, but the idea is like the solutions are vectors. So you have a vector that solves the system here. You have another vector that solves the system of equations here, and the convexity will say that any of like the vectors that end on this segment solve the system of equations. So that's infinitely many points, right? Because it's like a segment. So that is like an acute way to prove that there are infinitely many solutions. Once you have two or more. Um,
Professor?
yeah,
So can you explain, so you're saying that, okay, we have the kernel, like matrix, if AX equals 0.
right. That was a name that it was like when the vector was the zero vector here.
Yeah,
That was like, well, that the name for that was like a homogeneous system, right? uh, like a homogeneous like system of equations, but the solutions to the system of equations was called the kernel. Yes.
yeah, exactly. And then you're saying, what do you mean that K is not a vector space unless the,
Oh, because like if you remember when you defined a set, right? You could like there were like all these problems about like if I give you a set, can you check whether it's like a vector space or not, right? And to check that something is a vector space, you needed to check that the sum of two vectors is inside the space again. So the thing is like if you have two vectors here, like it's actually easy to see it like in this example. If you had two vectors here, oops. Where's my eraser? It always disappears and I don't know why. Up there, it's not already. Like imagine that you had two vectors that solve the system of equations, right, with 1, 2. So that means like you have a vector that solves a times x1, right, equals 1, 2. And you have another vector that solves a times x2 equals 1, 2, right? You have two solutions to the same system of equations. What happens if you add them, right? What is x1 plus x2? What does that solve? Well, you have to do a times x1 plus x2.
you're saying, yeah, so any combination would
Right.
solve it as well.
Well, but that's like what that is actually what I'm trying to say, because like,
Mhm.
imagine that you take the sum, right? If you do a times like the sum, like if you remember like the properties, like the multiplication, you distribute,
Yeah,
and then ax1 is 1, 2, right? And then ax2 is also 1, 2, right?
yeah.
And that gives you 2, 4, which is not 1, 2 again, right? So this does not solve the original system of equations, because to solve the original system of equations, it had to be 1, 2 here. So unless everything is 0, 0, 0, 0, because there is 0 plus 0 is 0, then that's fine. But the moment like one of these numbers is not 0, like you will always have this issue. So that's what I was trying to say. This is not a vector space unless you have a bunch of zeros, because like, like kind of like they kind of keep adding with
Okay.
Is that making sense
Yeah.
with everyone? That's kind of why the vector space property fails. So what I'm saying is that as a vector space, like this doesn't work, right? Like in general, unless like it's 0, 0. So it's bad, because usually we like vector spaces. What I'm saying is that even for something like this, even though it's not a vector space, it's convex. So convexity kind of survives in this case, even though we don't have like the vector space property anymore. So it's kind of like a replacement. You can think about it kind of like as a replacement to the vector space property. Like, we still want some being vector space is great, because then you can talk about dimension or a bunch of other stuff. We don't have vector spaces in many situations, like for many linear systems of equations, but still we do have convexity. So I'll show you how that goes here. Okay, so and it's like it's kind of like a similar proof to that, but you'll see what like the magic that happens now. So what is the proof? Okay, so suppose x1 and x2 belong to K. And this is kind of like this type of proof that I would expect you to know how to do, like, kind of like this type of like proof, like similar to like showing that something is like a vector space or not, like showing that something is convex or not, of like this style. So like, let's say you have two vectors that belong to the set K. What does that mean? Like that means that they solve the system of equations, right? That means that A times x1 equals B, and that A times x2 equals B. Oops, sorry, I'll put like the arrow on B. So far so good, everyone with me. So that's just what it means to have two elements of K, that you have two solutions to the system of equations. So now the crucial part, like, is that we want to show, right? We want to show that 1 minus lambda x1 plus lambda x2 is also in K, right? Because that's kind of like the condition for like the line segment to be in K, okay? Right? So what does it mean for this vector to be inside of K? That means that it must solve the system of equations. So this new vector must solve the system of equations. So this vector, so it must solve the system of equations. AX equals B. But what is that for this particular case? Notice that what is A times 1 minus lambda x1 plus lambda x2? Well, like again, like the matrix multiplication, the way it works, it allows you to distribute. So that's the same as A times 1 minus lambda x1 plus A times lambda x2. Right, so far so good. Does that make sense? And then like matrix multiplication allows you to take out the scalars and put them to the front, right? Like you can take out like a scalar. So this is the same as 1 minus lambda AX1 plus lambda AX2. Okay, so let me stop here to see if it's making sense. So far so good. Questions up to this point? But now we're getting there, because what is A times x1? We're assuming that we had a solution to the system of equations. So A times x1 is B. Okay, let me put it in colors. So this is B. And what is A times x2? Again, we are assuming that we have a solution to the system of equations. So that's also B, right? So you get 1 minus lambda B plus lambda B. But what is that? Well, if you just like, factor out the B, because like it's kind of like the same, you get 1 minus lambda plus lambda times B. So the lambdas cancel, and so you get 1B, which is just B. So that's like a new solution. that okay? Is that making sense? Questions up to this point, so far so good. So like you see, like the difference, like why this work versus this one does not work. Because in a sense here, when you are just, if you just do the addition, kind of like the coefficients keep adding. So you get one, like, that's why, for example, when we would double this number, like 1, 2 becomes 2, 4, right? Because you're adding it with itself twice. But here, when you do the combination, you kind of like are splitting B in pieces. So like you're taking like, for example, 75% of B here and 25% of B here. So they add up back to 100%. Like whereas here, like you're always taking kind of like 100% of B and 100% of B. And that's why the sum fails. Actually, this can be interpreted in terms of probabilities, because like probabilities are numbers between 0 and 1 that add up to 1. So 1 minus lambda plus lambda is 1, right? So you can think of like, oh, it's kind of like a probability, like, it's kind of related to like a fraction of like B, like the probability of like finding B is P1 and the probability of finding B on this side is P2 or something like that. But the point is like by kind of like partitioning in this way, you recover B again instead of like 2B or 3B or like some like a rescaling of B. So that's kind of like the cool thing like that works. That is why the convexity works. Um, whereas the other like the vector space property does not. Um, Is that okay? Is that making sense? So far, so good. Like okay, like let me just mention like some brief things, and before like continue, and then next time we'll continue with what we care. But there was nothing like special about the equality sign. So if I can replace everything with less or equal to, this would have like kind of like still work the same way. So why do I care less with less or equal to? Because those were kind of like the constraints that were showing up earlier when I had like this optimization problem. So like, but it's literally the same proof. You just replace equalities with less or equal, less or equal, less or equal. Like nothing like you know, kind of like changes too much. So like just like as a remark, like a similar proof works to show that is convex. Okay. And this was important. This is kind of more important because like this is kind of like the way in which like we were writing the inequalities for like the optimization problems. So what that says is like what I'm trying to say is that to connect it with what we're saying, like what I was saying in the previous two classes. So how does this like the connection with earlier classes? Is that the constraints, like the constraints to the optimization problem always form a convex region. So the constraints to the optimization problems that we care about, to the optimization problems we care about form form a convex region. Okay. And by the way, this particular set is called like a polyhedron. And so I should mention that. So a polyhedron is just basically like the type of convex sets that appear when we in this course, like polyhedron. Let me see actually if there's like a cute pictures of polyhedra here. Sorry about that. All right. Well, yeah, these are kind of cute. Like these are like, so they're kind of like, have like corners and edges, things of that sort. Well, this is kind of very pretty. But like so they are like interesting shapes. So like let me see what's happening here. So yeah, if you go down to Google, you see that they have like a very nice geometry, like but there's a lot more like variation in terms like of how the sets look like compared to vector spaces. Because if you remember like vector space, oh, that is kind of cute if you want to buy some to play around. So oh, these are really pretty. Ooh, I'll try to find them online. But yeah, so they're cute. So
Professor.
yeah.
So, the constraints that we saw like last time, they formed a polyhedra, right?
Correct.
And then, like, if we looked at the picture,
Mhm.
like, there's
Oh.
a couple of like 3D ones,
Mhm.
like, it wasn't like a 3D one, like if you do the 5 platonic solids.
Oh yeah, like where like the five. Oh, this one, yes.
Yeah, like, we're not doing like the last one, right? Or like,
Well, I mean, we don't. That's a cool thing about the method that we'll see later. We never actually bother of how they look like, so we don't care about how they will look like. Of course, like yes, in practice, okay, right. This probably would be outside of the scope because this is probably defined by a lot of inequalities, and we don't want to work with something that has so many inequalities for our purposes. But again, like you know, these like probably like for any realist again like kind of like in the real world like the linear optimization problems have like hundreds of inequalities or thousands of inequalities with thousands of variables. So these are like pieces of like nothing compared to like the real polyhedra that you would. And the thing is like they're in 5 or 10 or 20 dimensions. So but it's kind of they're spiky and they kind of look like this, so you cannot visualize it. But the kind of like the what we would do is kind of like circumvent all the picture approach because like it's kind of like very like not realistic to work with that in practice, but it's still kind of nice to see kind of have like an idea of like kind of like think that like convexity also, because if you imagine putting 2 points, the light segment is always inside them, that type of thing.
okay,
Yeah,
thank you.
yeah, no, of course, like the so yeah, and the Platonic solids are kind of special, like because like they had been known since antiquity, and like I think at the time of Kepler, if you remember Kepler's laws, they only knew like 5 planets, at that point, and so Kepler kind of like in a mystical way he tried to fit like the planet trajectories inside Platonic solids because like the Platonic solids were like kind of like the big thing. So like kind of like it was like a big thing like to try to kind of like the people who like also like find like secret codes inside the Bible, like there's all this like numerology kind of like industry like that, like like that people think that there's certain hidden messages in the Bible verses like in terms of numbers. So it's kind of what Kepler was doing, kind of like a similar thing where like because they only knew 5 planets at that time, then they had to have like a mystical feeling meaning because like you can show it's kind of like one of a big theorem in Euclid that there are only 5 perfect solids, which are like these 5 Platonic solids. So it was okay, that must mean something like in terms of like the design of the solar system. So I mean you can kind of like get it. I'm just saying they were so cute that they were like being given like all these like mystical interpretations. Like now no one cares about them per se, but again, well, I mean, of course, unless you're a mathematician. But I'm just saying like they don't carry like the same weight. Oh, a Platonic solid, but they're still very pretty. So okay, we're almost done. I'll kind of give like the last definition, and then next time I'll start with that. To kind of like exploit it, but this is kind of like the key because what did I say? And this is actually like very clever definition. Um, what did I say before, like at the beginning, when the max and the mean happen at the corners of the polyhedra, right? So recall, max and the mean occur at the corners of the polyhedra. I don't know if you remember with the farmer's problem, right? We had like this kind of like region, and the max was one of the corners of like the region. Okay, so it would be nice to have like a nice characterization of like a corner, like or like in these terms of convexity. And there's like actually like a very elegant definition, which is called like an extreme point, which I'll review next time again. So like I'll just give you throw like the definition for you to look at it. So a point inside a convex set convex set is called an extreme point. And you should think of this kind of like some sort of corners. If it is not a convex combination of two only combination of two other points of K, two other points of the region. So I'll kind of draw a picture of what I mean, and I'll finish here. I'll do like a non-example and an example first. Okay, so let me do first, let's take something that's convex like a square, actually. Oh, more like a rectangle, I guess, in this case. Okay, so if I take a point on the inside, right? Let's say I take a point on the inside. My claim is that point is not extreme. So I'm going to say that P is not extreme. Okay. Why is P not extreme in this definition? Because I can find two other points and I will have tons of options, but I can find two other points. Let's call them P1 and P2, right? Oops. And you see P is now kind of in on the line segment from P1 to P2. So now I kind of put P and like I kind of was able to draw a line segment passing through P. Okay, and those 2 points P1 and P2 are inside the set. Actually, I mean I'm thinking about the like the square, like the rectangle being colored, because I do need to consider like the the inside of the region. So what I'm saying is that this is not extreme because there's like a connect, like, it is part of like a connecting line segment between the 2 points. Which is good because, like, if you remember, I had told you that the max or the mean could never occur at the interior. So it's good that this is kind of like excluding the interior like altogether. Like, it's very easy to convince yourself that there's nothing special about the square. You only needed like a little bit of room in both directions to kind of like draw the line segment. And this is not like the only two that I could have drawn, right? Like, if I didn't had wanted to choose those two particular points, these other 2 points, like for example, would have worked. Like just rotate the line segment a little bit, if you know what I mean. So like there's plenty of options. It's not that there's only one option that works, but this also would have been giving you like a line segment that kills it. Okay. What about like some point on one of the edges? Like I'm almost done, sorry. So just like a few more minutes, 2 more minutes. So say, what about one point here? Let's say if I got chosen P there, you still can take advantage of this edge to find 2 points, right? That make it like as a convex combination. So for example, if I got chosen again, like P1 here and P2 here, right? There's still like this line segment that passes through P. So far, so good. So like in these cases, P is not extreme either. Is that making sense with everyone? Like, are we okay with that? But so what would be the extreme points in the square? Literally the 4 vertices. Like if you think about let's copy paste, and that's the last thing that I'll draw today. If you think about like an actual corner, right? Think about like an actual corner here. This is extreme. And again, it's kind of like one of those things that you have to play like with your imagination first to see, like, try to draw like a segment with 2 points like on the square that kind of passes through the corner. You cannot do it, So there's no, like, of course, like this is kind of like a proof by picture, but there are like other ways to there's no like segment you can draw like inside the square that would pass through the corner. Okay, now, and this is super important because there's like in the case when the convex set is kind of like a solution to the systems of equations, there's like a very elegant way to characterize that in terms of the matrix. So that's kind of what makes all the theory work nicely. So I'll tell you more about that next week, because that's kind of like the key that will kind of like get the ball rolling with the simplex method. Just before we wrap up, I will send you like an announcement about that tomorrow. But my idea, as I said, I'm going to write some problems for you to work on. And again, I still want to add some more tomorrow, but like, so I'll send you like an announcement once I have updated the list. So basically, and then like I'll ask you to upload some of those for them to be graded. But basically the terminology is like, if I put like a smiley face next to a problem, that is a problem that I'm expecting you to know how to do, and that is kind of like what I would call like an exam type problem. If there's like a frowny face, like it doesn't look very clear here. It's kind of like a more like, like a problem that I wouldn't be interested in asking you, but like, if someone wants to kind of dig deeper into the course, that is kind of worth checking out. Even if I wouldn't at least read them, even if you don't want to try them, because like you would learn like useful facts. Like I will put like in the frowny faces, like interesting stuff. So, I mean, the others can also be interesting, but again, once I have updated the list, I'll send you like a reminder, because, I still wanted to add some more